what I'm going to do is explain resistive RAM method of Boolean logic that is made on this paper, and my project in the end is going to implement all the logical operations from that the paper proposes and make an adder after this. So So the motivation behind this project that the paper is about is that there's a lot of idle time, CPU idle time, while it waits for information from memory. And it has to wait for information from memory because that's the von Neumann architecture that separates memory storage from the logic unit. So there are attempts to make a new architecture that joins the two. And this method uses resistive RAM. And resistive RAM is a kind of RAM that changes its resistance according to parameters input and interface. And this group developed a device. Here's what I just said. This group developed a device that has the resistive RAM up here connected to a NMOS gate, and then it has three inputs, and it has an output by measuring the resistance of the device. And they showed in the paper that with this they naturally have a NAND gate. This on its own already has a NAND gate. So if you have a NAND gate, you have everything else. You can use several NAND gates to make NOTs and XNORs, whatever. Therefore, this device alone is already Boolean complete. And the way they show that this is an NAND is with this three-step diagram. So their device has to be initialized in an initial step in order for it to be able to input any bit in it. So the bit in the end is going to be the resistance, and they have to initialize it by setting the top input T1 and the gate, closing the gate for 1, and grounding the T2. This allows the device to change its resistance. If you don't do this, it won't change the resistance. Then you can set your parameters as P and Q is a 1 or 0 on the gate and on T2, keeping T1 0 closed. Then that will change the resistance of the device, and then you have it. So they show in this image, and they have others in the back, but I thought it was too complicated to bring up here. That setting them to P and Q to 0 will keep the resistance at 1. Either of them being 0 and the other one same, and they are both being 0, the resistance goes to 0. So it's an AND. The issue with this device is that it's really big. If I go back to the previous image of it, it consumes a large area for the device. That's the issue they point of their device. But it's not volatile, so if you read whatever the resistance is going to be, you don't change it. That's an issue with other similar devices. So it's stable. And it's quick compared to other devices that they talk about in the paper. I mean, it's kind of weird to have a starting step, in my opinion, but it ends up being quicker than other devices. So what I'm just going to do is get the device and make schematics for all possible logical gates with it. So actually draw the and not and all the others. And then using those, also make a schematics of another, I'm not sure yet, if a ripple carry or a look ahead. And also some kind of pseudocode for the process. Because it's going to be a bit different than usual because of the initialization step. So every time you have to change something, you have to initialize, change, and then you can carry on. And that's about the short presentation.
I really appreciate your the text style slides.
Thank you.
And I don't think you can create a combinational logic for the adder, which means that you apply the input on the input signal. You apply input signal on the inputs, and then you can get the results in the same cycle. But you need to design some adder with clock. For example, in the first cycle, you do some logic like the last figure you showed, do some XOR or NAND operation, and then in the second cycle, you did some logic again, and maybe after 32 cycle, you can get the adder result. You know what I'm talking about? Okay.
Yeah, but my plan was using several of these devices
to support multiple beats adder.
Yeah.
But still for one adding operation, you still need a multiple cycle to finish that. I think if you can understand the figure you show, you can finish this.
Yeah.
This is a relatively, yeah.
I have a few doubts. One question actually. Looking at this, my feeling is, because the way you read the signal out is that you apply a small voltage on the T1, 50 millivolts compared to 1 or 2, that is the usual, and the resistance is on kilo ohms. So if you read, my intuition would be to read the current ST2 instead of trying to read the resistance. But that's just a technical thing.
I mean, you don't need to worry about the read operation.
Yeah.
When you finish step 1 and step 2, the result has already stored in the cell. If you don't need the result, you don't even have to read them out.
Yeah. Yeah, but the way they read it is measuring the resistance, right?
That's right. Okay. That's right. To decide whether it's a 0 or 1 in the cell.
Yeah. No, it's just my feeling, because my background is physics, so my feeling would be that it would just be easier to read the current. But it's just something that came.
But again, you need to apply some voltage so that it has some current.
Yeah, they are equivalent. But
yeah. So in the final algorithm, you need to clearly write each step. What's the P and the Q in each step? I think that's enough.
Yeah.
Okay. Thank you.